In this video, we're continuing to work with the Xbox Kinect2 sensor and the Natural Interaction toolkit in openFrameworks, and I build a particle painter and make green dots shoot out of my left hand. Hey everyone, welcome. We're back again. We're carrying on the work looking at the Kinect2 sensor and openNI skeletal tracking natural interaction toolkit using openFrameworks. The last time we downloaded and installed the openFrameworks C++ add-on for openNI2, the Open Natural Interaction Toolkit. The URL's on the screen right now. We downloaded the add-on, we made it available to openFrameworks as a library, and we got it running, and we found that we could do skeletal tracking. We've added in our openNI 2 add-on and openFXNI2, and if I run up this and compile it, you can see I've got my Kinect sensor set up just over here, and when this compiles, it'll load up, and you can see we have our skeletal tracking model. We're using the 3D tracker, and this allows us to use the easy cam to look around, so I can see myself from above, and allows me to see the skeleton from different viewpoints in exactly the same way that we saw in previous videos, being able to look at a point cloud from any virtual camera angle. What I want to do in this session is dig a little bit more into what we can use the skeletal tracking for and how to access some of the information inside it. So looking at our header file again, we've set up an openFXNI2 device, which is to be able to talk to the Kinect sensor, and then we've set up a tracker object which will interpret the data that's coming from the Kinect sensor. In our CPP file, we open up our device to talk to the Kinect sensor, then we set up a tracker and tell it to use the information from that Kinect device. In our exit, we remember that we want to close the connection that we've made to our tracker and our device, so we shut the Kinect sensor down over USB. And in our update, we're just saying update and get information from the device. I've added a couple of pieces in here that I'm going to slowly walk through to allow us to do a little bit more, but I've commented them out for now. So in our update, we just update the device to see if there's new information from it. And in our draw routine, we looked previously at how we could draw the depth pixels and the depth texture that we get from the Kinect, or we can draw our skeletal tracking in 2D, or we can draw it in 3D. So here we're saying begin the easy cam, which gives us the ability to look around our 3D view. It's a built-in draggable view, and we're saying to the tracker, please draw in 3D. Then we're going through and looping and asking the tracker here, please go and tell me how many users you've found in your viewpoint. It loops through in a for loop, and we ask it to make a reference each loop to say, get a reference to the user that you found. If you found 0, then there'll be none, 1 or 2 or 3 or 4. So each time we go through the loop, we say, find me the next user in the viewpoint, find me the next user in the viewpoint, please. And this reference of user allows us to then go through and ask for parts of that skeletal body that it's seen. And it also allows us to record how many people can we see in the picture, which is something that we can't do very easily using depth pixels because we don't know whether this blob is a chair or is a person. So here it's explicitly looking for a skeletal shape, and when it finds one it says I've registered this as a user. So if you just want to know how many people there are, you could use this and say how many users have you found, and every time it finds a complete skeleton it'll add that to the number of users. So what we were doing last time is we use this reference to the user and we say please go and get a joint from the user because it has this idea of a skeletal track, and the joint that we want to look for is the head, and load that as a reference in the variable head. And here we're setting our color to red. We're saying go and find out the transformation in space, the GL transformation in space of where the head is. And what happens is the body is rigged, the head being the parent piece that the neck is connected to, the shoulders are connected to, the arms are connected to the shoulders are connected to the torso, the legs are connected to the torso, and so on, and the hands are connected to the arms. So everything is linked through. And what we can get is a reference to the head as its specific place in world space, and then everything else is relative to that. So if we get the position of the head, we can say, find where that is in world space, move over there, and then we're going to ask it to draw a box, and then just pop back to where we were, like a push and pop in our matrix. And that's all we do. And then we end our 3D cam, and then at the bottom, we have our debug using draw bitmap string, and I have got it to print out the frames per second that the tracker is running at, the frames per second the application is running at, and I've added one more thing in to say, just show me the number of people, and it uses this tracker get number of users routine to return us a number 0, 1, 2, 3, however many it can see. So let's run that now and see what we've got. So the Kinect is searching. Excellent. It's tracked me, it's found me. I'm asking it to say, get the number of users, and if you can see on the screen, the number of people is 1. It's finding where my head is, and at that position, drawing this big red box. So what I want to do is go and change some of that and add some things on. So I'm going to make a tracker that tracks my hands and allows me to do things with the position of those hands. So the first thing that I want to do is get rid of this ugly red box, and I want to say OF draw sphere, and it's going to ask for a particular location. I can pass it, because it's what's called an overloaded function, I can pass it sphere location radius. In this instance I'm just saying draw a sphere implicitly at 0, 0 of a radius of a little smaller, 100, and here above it we've got OF set color, so this will be the color that the sphere is going to be drawn in. I'm actually going to set it to be 255, 255, 255. So now it's going to set the color to be white, transform to the position in the world where the head is, draw us our sphere, and then transform back again using this transform and restore transform. So there I have my skeletal tracking, and this time I have a nice big white pumpkin for my head, which I much prefer the look of. And you can see it's drawn in wireframe. So I've drawn my head as a large sphere, and I've used it by saying find a user from the number of users that the tracker can see in the image, go through and get the joint from that user, and I can use a named joint, which is head, and there are many others that it knows. And the next thing that I want to do is actually go through and ask this tracker that's made a user, found a user in the image, can you go to the user, get the joint for the right hand, and put it into this variable right hand. And the same for left hand. Go and get this named joint left hand. And now what I'm going to do is say, if I uncomment this, for the right hand, I'm going to set the color to be red. I'm going to go to the right hand, and one of the properties is get global position, and it gives me an X, Y, Z position of where it thinks the center of the right hand is. I'm going to put it into right hand position, which is an OF vector 3, so it's just an object that has an X and a Y and a Z in it. I've made a variable of vector 3 type for left hand position and right hand position, declared them just here. And I get the position of the right hand that I've requested from the tracker by saying, have you found a user? Tell me where the right hand is, put its position in here. And at that point, rather than transforming to it to show you a different way of doing it, rather than using the transform GL from the head that we have here, I'm going to say get the XYZ position into our vec3 variable, right hand position, and draw a sphere at that point, 20 pixels in size, for my right hand, and I've just set the color to be red. So all being well, I can track my right hand now, and I have this vector3 variable with its XYZ position in it. So let's run this and see what we've got. So we have our Kinect sensor, and there it is. I have my white head, and I have my right hand. And the right hand is having a sphere drawn there, but I've extracted the data from the skeletal tracking, and now I have this variable, right hand position, with X, Y, Z data in it, and I'm just telling it to draw at that point. What I've also done in code is I've asked it to draw my XYZ data using OF draw bitmap string, and I tell it to draw some text at a particular position. So the position is this XYZ position in space represented by the vector3 variable right hand position, and I'm saying get the right hand position, turn that from being XYZ into a string that we can print out, so it turns it into text, and I use OF draw bitmap string. I'm going to do exactly the same for my left hand. So up here in my draw routine at the beginning, I've declared a vector3 variable left hand position, which will hold the X and the Y and the Z position in that variable. And I've declared a couple of colors here saying the variable red is this, the variable blue, variable green. So I've declared the colors here. Which means I can reuse them, and if I fancy changing them for a different color, it's very easy. I'm going to come down and say, for my left hand, get the left hand position from global position, and again here I've said, go to the user that the tracker has found, get a joint from it, go to joint left hand, and it shows you the center position of that. And we pull that out and put it into our variable left-hand position. This time we set the color to be green, and we draw a sphere at the left-hand position, and I'm going to draw a bigger sphere, and I'm also going to tell it to draw out the bitmap string. So I should have a red sphere and a green sphere, and next to each hand, printing out the XYZ position of each hand, which is really, really cool. The point of doing this is to show that we can draw things unrelated to the skeleton tracker by extracting information out. And then we have this data that we can do other things with. So let's run that up. And my Kinect sensor has found my left hand and is drawing a big green sphere. My right hand is drawing a red sphere. and at each point in the model, for both my hands, I'm getting the XYZ data from it, which is exceptionally cool. So now I can do different things with it. And what I'm going to do is, I would really like to be able to shoot green sparks out of my left hand. And to do this, I'm going to use a particle system. I've covered particle systems previously, but it's a really simple way of generating swarms of objects. In this instance, I'm just going to make lots and lots of dots that come out of my hand with a random direction and fade out after a period of time. Have a quick look through some of the other videos, and I'll post a link here about using particle systems. I've copied and pasted this simple one in just as an illustration of how we could use something like skeletal tracking for making painting programs or musical programs by extracting out the information from the skeletal tracking and translating it into something else. So the particle system that I've added in, if I go to my header file, at the top, I've made a new class called particle. And when I make a particle, the constructor here wants to be told a vector 3 point for its start point of the particle and an OF color, the color of that particle. So when I make a new particle, I say exist starting at this XYZ point and be this color. In the description here, I've also got a function I made called update, which will just update where the particle is each frame. And then I've got a routine to draw the particle, so I can, in my update, say update the position of all the particles I've made, and in draw all the particles, please. And there are a couple of things that this particle knows. The particle knows its location, which is vector 3. It knows the direction it's traveling in, which again is going to be a vector 3 for XYZ direction, and then a velocity, which is the speed at which it's pursuing that vector, that direction it wants to go in. And then I have an integer for the size of the dot, and then a color for the color of each individual dot. In my OF class, now that I have a particle object, I want to make a big list of them. So I've made a new vector, which is a big list, to put a particle into, so that I can make many, many particles and address them all in one go, rather than saying particle 1, particle 2, particle 3. I make as many as I like, and I stuff them into this vector in a big long list, and then I can just say go loop through all the things in the list and update the particles or draw the particles. So in my header file, I've set up my particle class, and in the update, I'm going to go through and say, have a look in this for loop, how many particles are there inside the particle vector? So what's the size of that vector? So loop through starting at 0, go through how many particles there are, incrementing I, and then I address each individual particle in the particles list by saying particles position 1, position 2, position 3, position 4, position 5, etc. Update. I do exactly the same in my draw routine. If I come down and then comment this, so I'm using almost identical code. I'm saying make a for loop that goes and finds how big the particles vector is, so particles.size. It returns me that, and I say loop through however many positions there are in the particles vector, and tell particle I, 0, 1, 2, 3, 4, 5, etc., to draw itself. So the particle knows how to draw itself. It's one of the routines that in the header file we declared that the class of particle understands. It understands how to draw itself. So in my CPP main file, if I scroll down a little bit, I've pasted these in. Here is the routine that a particle understands when it's told to update itself. It gets its location and it adds direction times velocity to the location. So it says, where am I? What's my direction? And how fast should I be going there? Add that to where I am now. So update my current location. Every time I tell a particle to update, it works out where it should be next, where it should be next, where it should be next. Also, when I tell a particle to draw itself, it knows how to draw itself. The first thing it does, it says push style, and this is like push and pop matrix. It freezes everything in the world, but this just freezes the drawing style for the color and the fill and so on. So if I'm drawing something somewhere else, I don't mess it up and have to reset it. Here I just say freeze the drawing style for the whole world. Set the drawing style to be fill because I want all my particles to be filled rather than outlined dots. Set my drawing color to be able to be whatever the color of this particle is. Draw a circle at whatever the location of this particle is, at whatever size the particle is, and then pop style. Unfreeze all the styles, so return them back to what they were before I told this particle to draw itself. And in the particle constructor, this gets called when I say, please make a new particle. I pass it the parameters for an openFrameworks vector3 object. So it's an XYZ object variable called start point. I pass it a color called new color. And then inside it, I set the speed. I tell the color of this particular particle I'm making to be new color that I've just passed it. I'm setting its size to be 10, but I could randomize them, and in other versions I've said if the particles are fast, make them small, and if they're slow, make them big, so they act in a physics natural world type way. I set my location to be the start point, and then I choose a random direction in X and Y and Z. And then I choose a random speed or a random velocity in the XYZ direction. So I generate a particle. The particle knows how to update itself and knows how to draw itself. So to recap, in our update, we loop through all the particles, tell them to update themselves. And at the end of our draw loop, we tell all the particles to draw themselves. Now we need to make some particles. And what I'm going to do is, here in my draw loop, where I've said get the number of users, find out where their hands are, where I'm drawing my left hand. So I'm drawing my left hand as a big green sphere. I want particles to come flying out of my hand. So I'm going to, if I uncomment these two lines, openFrameworks now knows what a particle is because I've defined it as a class in the header. So I can say, make me a new particle called new particle. Make this particle exist, because we need to tell it where to exist, where to start from. The left hand position, which we're using just now to draw our green sphere. Grab the left hand position, wherever it is now, make a new particle there, and tell the particle to be green. Take this new particle, and one of the things that you can do with a vector is say, push this new thing onto the end of you. The vector, or the list that we have, is of particles. It's called particles, which is kind of confusing, but there you go. And I'm saying push this new particle onto the end of the list. So add another particle there. So when my hand moves around, every time we do the draw loop, it's going to say, find out where my hand is, make a new particle, add it to the list of particles. And then when I draw, there'll be an extra particle at that position to draw. So let's see what we have. And there I have my right hand with a small red sphere, and at my left hand, as I move it around, it's making particles. All coming out of my left hand, which is kind of cool. And if I run this up full screen, I move the viewpoint to above, you can see the particles being generated in 3D. But we've also got a bit of a problem. As I'm making thousands and thousands and tens of thousands of particles, this is starting to slow down, and the particles that are off the screen I don't need anymore. And also the particles are kind of filling up the screen and it looks a little bit messy. So I want to do two things. One is, after the particles have got to a certain age or I've made a certain amount, I just want to start getting rid of the old particles. So the first thing that I'm going to do is I'm going to decide what is the maximum amount of particles I need. So in my header file, I'm going to declare an integer in the off app, which means that all of the functions in OF app can get to it. So I'm going to say, what's the maximum particles? And then in my setup here, I'm going to say 1,000. Yeah, 1,000 particles. That's the maximum amount of particles I want. And then in update, after I've said tell all the particles to update, I'm going to say how big is this vector of particles. So I say what's the size of it, and if it's greater than my integer max particles, which I set to be 1,000, so if there's more than 1,000 particles in the vector, I'm just going to say erase particles begin. And particles begin is the first position in the vector of particles. So I'm going to basically say particles, erase the first one, please. So when we hit 10,000 particles in total, I'm just going to start erasing the first one on the list, which means the older ones get deleted, which means my list of particles never gets bigger than 1,000 or max particles, which is really good. And then what I'd like to do is I'd like these particles to fade out a little bit. Now, every particle has an individual color, which is an RGB. It has an RGB value, or as we saw in previous videos, you can set it as hue, saturation, and brightness. Here we're setting RGB. We've set them all to be green. But in my update, I'm going to add one more thing. So in the update routine, I'm saying go through all of the particles and tell them to update. And what I can do here is I'm also saying each particle change the color A for alpha value. So when you say color, you can say color.R is the red, color.G is the green, color.B is the blue value, or actually the alpha value of each color. So I'm saying color.A is the alpha, and minus equals it, i.e. subtract this from it, 0.001. So make it a slight bit transparent, and every time you run this loop it'll keep doing that, and then at some point the array will get to 10,000 and it'll get deleted. So if we run this, let it compile, we should see only 10,000 particles, and they should fade out as they get older. So there's my particles. That's great, the screen is not filling up, and you can see, let me run this to full screen. The particles are fading out as I move about. And over time, they're being deleted from that array of particles. Now, this is very good, and I can make particles all over the place. But what would be nice would be able to control the particles. So in the next video, I'm going to show you how we can use different information to control different parts, and I'm going to make myself a particle painting theremin. So join us on the next video, hit the subscribe button, like the video, give us suggestions on what you would like to see, and you can also get the source code from the link down below.